Tonight, we embark on a tranquil journey, drifting through the cosmic currents of our universe to uncover the extraordinary story of our own planet, Earth. We will explore the ancient echoes of creation, witness the birth of stars, and trace the improbable chain of events that culminated in the vibrant, living world beneath our feet. It's a tale of immense scale, of forces beyond our comprehension, and of the delicate balance that allows life to thrive. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Our home, this singular blue marble suspended in the vastness of space, is truly a wonder. It is a world teeming with an astonishing diversity of life, from the smallest, unseen microorganisms to the towering forests that stretch towards the sky, and of course, ourselves. When we gaze upon Earth from the silent vacuum of orbit, it's an overwhelmingly beautiful sight. Every known form of life, every intricate ecosystem, every civilization we have ever built, exists within the thin, delicate envelope of its atmosphere, clinging to its surface. This perspective, seeing our entire known existence encapsulated in a single, swirling sphere, can be almost too much to fully grasp. The sheer vividness of its blues and greens, the swirling whites of its clouds, all set against the profound blackness of space, paints a picture of unparalleled beauty. Our planet holds a unique place within our own solar system, a true anomaly among its rocky and gaseous siblings. But this raises a profound question that has captivated humanity for generations. Is our Earth truly unique in the boundless expanse of the entire universe? Or are there other worlds, perhaps countless others, that mirror its life-sustaining properties? To even begin to answer such a monumental question, we must first unravel the intricate history of our own world. We need to comprehend the precise conditions and the remarkable sequence of cosmic events that conspired to bring Earth into being. By understanding the genesis of our planet, we gain a vital blueprint, a set of cosmic criteria that we can then use to search for similar environments around other distant stars. If we can identify these specific conditions elsewhere, it would strongly suggest that other Earth-like planets, potentially harboring life, could be forming or already exist across the cosmos. To embark on this quest, we must journey not just across vast distances of space, but also back through the immeasurable depths of time itself. Let us rewind the cosmic clock, not by a few centuries or millennia, but by a staggering 4.5 billion years. In that unimaginably distant past, the nascent solar system bore little resemblance to the familiar arrangement we know today. Instead, we would have witnessed a scene of nascent chaos and potential, a minuscule speck of cosmic dust, almost imperceptible amidst a swirling, gargantuan cloud. This tiny fragment, almost poetic in its insignificance at that moment, was destined to become our Earth. It was just one among countless other dust particles, all coalescing within a colossal, diffuse cloud of gas and dust, what astronomers affectionately term a stellar nursery. Within this vast, dark expanse, the very first, fundamental steps of planetary formation were about to commence. This was an event of such monumental significance that it would fundamentally transform the entire cloud, giving rise to thousands upon thousands of nascent solar systems, each in its own delicate stage of infancy. And among these countless new stellar families, our own sun and its planets would begin to take shape. It's a process so fundamental to the universe that it isn't merely a relic of our past, it's a phenomenon actively unfolding even today. Thousands of light years away, nestled within the magnificent Eagle Nebula, the very same mechanisms are at play, painting new cosmic landscapes with the birth of stars and worlds. Our own solar system, with its familiar sun and orbiting planets, was born from just such a colossal cloud of gas and dust. Within the heart of nebulae like the Eagle Nebula, Astronomers have observed majestic structures, often referred to as the pillars of creation. These aren't merely small wisps of gas, they are immense, towering columns, each stretching for trillions of miles through the interstellar medium. Though they appear incredibly dense and solid in images, these gas clouds are, in fact, remarkably tenuous. Imagine trying to gather enough of this incredibly sparse material to form something tangible. You would need to compress a volume equivalent to an entire mountain range, squeezing it down with immense force, just to create a single, tiny rock, no bigger than the palm of your hand. This illustrates the almost unfathomable emptiness of these vast cosmic nurseries. To transform such diffuse, ethereal gas and dust into the incredibly dense, solid forms of stars and planets requires an event of truly supreme power, a cataclysmic force capable of overcoming the inherent sparsity of the cloud. Such an event, it turns out, can only follow one of the universe's most dramatic phenomena, the spectacular death of a giant star. In 2007, the keen eyes of the Spitzer Space Telescope captured a revealing image that hinted at just such a force. It revealed a searing ball of hot gas, positioned ominously behind the pillars of creation in the Eagle Nebula. This wasn't just any gas, it was the unmistakable evidence of a colossal star that had exploded, unleashing a vast, invisible wall of superheated gas and energy, now racing relentlessly toward those majestic pillars. This approaching wave of scorching material, observed to be hurtling toward the pillars of creation, is widely believed to be the shock wave from a supernova, the explosive demise of a truly massive star. Supernovae are cosmic events of unparalleled violence, so brilliant and energetic that, for a fleeting period, they can briefly outshine entire galaxies, pouring out more energy than our Sun will produce in its entire lifetime. During such an explosion, superheated plasma, a state of matter so hot that atoms are stripped of their electrons, blasts into the surrounding space at speeds reaching an astonishing 70 million miles per hour. This mighty, unseen shock wave, a ripple of raw cosmic power, speeds inexorably toward the pillars of creation. When it inevitably collides with them, it will not only demolish these vast, delicate structures, but in a profound act of cosmic recycling, it will also instigate the creation of entirely new worlds. The titanic impact of these supernova shock waves into the pillars is a crucial step. They smash into the diffuse, thin gas and dust of the nebula, compressing it violently into incredibly dense clumps. Each of these newly formed, compact knots of matter represents the embryonic beginnings of a new star, a new solar system. It's a breathtaking cosmic cycle, a quiescent molecular cloud, seemingly minding its own business, is suddenly and violently blasted by the immense energy of a supernova explosion. This crushing force then initiates the gravitational collapse, leading directly to the formation of fresh generations of stars and their accompanying planets. Let us once more wind back the cosmic clock, returning to that pivotal moment 4.5 billion years ago. Our own solar system, the very cradle of our existence, began in precisely this dramatic fashion. A supernova eons ago delivered a crushing blow to a massive, dusty cloud of gas. This immense compression transformed the nebulous cloud into a swirling, flattened disk, a protoplanetary disk. What was once a thin, diffuse expanse of material became a dense, rotating whirlpool of gas and dust, a cosmic vortex where a solar system was actively in the making. In this incredible cosmic exchange, one star met its fiery end, only for a new star, our Sun, to be born, surrounded by the raw materials that would eventually coalesce into its family of planets. This violent, yet ultimately creative, event marks the very first link in the long, intricate, and profoundly unlikely chain of cosmic occurrences that ultimately led to the formation of our world. For Earth to even exist today, for us to be here, we had to overcome truly astronomical odds. A multitude of incredibly specific factors, a delicate cosmic alignment, had to converge with improbable precision to produce a planet precisely like ours. We require the right distance from our parent star, a perfect size to retain an atmosphere but not become a gas giant, and even the presence of the right kind of moon. On Earth, by some incredible cosmic stroke of luck, all these conditions are exquisitely balanced, creating an environment perfectly calibrated for the emergence and sustenance of life. To achieve a world like ours, it's as if the universe had to deal us a hand full of aces, a perfect, winning combination against staggering odds. Somehow, our solar system managed to hit that cosmic jackpot. But the enduring, magnificent question remains, did this extraordinary roll of the dice happen anywhere else? The birth of our planet, a world now teeming with intricate life, was paradoxically triggered by one of the most violent and destructive events in the universe. A sparse cloud, gently drifting through the void, was violently crushed into a dense, swirling vortex of dust and gas. A significant portion of this humble dust, this cosmic detritus, was destined to become the very substance of planet Earth. But how, we might ponder, do these almost infinitesimally tiny dust grains, far too small to exert any meaningful gravitational pull on each other, somehow aggregate and grow into entire worlds, into planets of immense scale and complexity? The chain of events leading to Earth's formation, initiated by that distant supernova explosion, is a fascinating progression. At the very center of this swirling protoplanetary disk, a hot, glowing ball of gas began to accumulate and grow. This central concentration of matter, compressing under its own immense gravity, was slowly but surely igniting, destined to become our Sun. Around this burgeoning protostar, the remaining dust and gas continued to swirl, forming the raw material for the planets. But before these planets could truly take shape, these tiny, individual dust grains had to find a way to stick together. This presents us with an intriguing conundrum. The protoplanetary disk, at this early stage, consisted of gas and dust particles, many of them no larger than the microscopic particles found in smoke, like those from a cigarette. These were truly minuscule things, and yet, from these almost invisible specks, we needed to arrive at the immense, solid, and complex structures that we now observe on Earth. We understand that gravity is a profoundly powerful attractive force, capable of shaping entire galaxies and holding solar systems together in their intricate orbits. But these individual specks of dust are far too small to exert any significant gravitational pull on each other. They simply lack the mass. So, if gravity isn't the binding force at this initial stage, what mysterious mechanism allows these tiny, disparate dust particles to clump together and begin the long, arduous journey of forming planets? To unravel this fundamental mystery, scientists in Germany have embarked on an ingenious quest, conducting experiments that aim to simulate the peculiar behavior of dust in the unique environment of space. Their laboratory is housed within a colossal tower, designed specifically for this purpose. Here, they conduct what are known as freefall experiments. The entire experimental setup, including their carefully prepared dust aggregates, is placed into a state of perfect freefall. This ingenious method creates a microgravity environment, closely mimicking the weightless conditions that these dust particles would experience in the vast emptiness of space. It's an incredibly precise and effective simulation, one that many researchers consider to be the closest approximation to actual space conditions achievable here on Earth. Within this specialized facility, researchers meticulously place samples of dust into a robust container. This container is then loaded into a launch capsule, positioned at the very base of the towering structure. From there, it is propelled upwards by an incredibly powerful catapult. This catapult is capable of launching the half-ton capsule from a complete standstill to a speed exceeding 100 miles per hour in just a quarter of a second. an astonishing acceleration. The capsule hurtles upwards, reaching the apex of the 400-foot tower before gravity inevitably reasserts its dominance, pulling it back down towards the ground. Its descent is cushioned by a massive drum filled with polystyrene balls, a soft landing pad some 30 feet deep. This entire, elaborate process, from launch to cushioned impact, provides a precious window of approximately 10 seconds of true zero gravity. This brief, fleeting moment, they hope, is precisely enough time to observe how the dust particles interact and, crucially, how they begin to stick together. With a final countdown 3, 2, 1, and go, the capsule is launched. Moments after it begins its ascent, the dust particles inside become weightless, suspended in a state of microgravity, and remarkably, the experiments confirm their hypothesis. The grains do indeed begin to clump together, just as they would have done in the earliest moments of our solar system's formation. These images, captured during those precious seconds of freefall, offer invaluable insights, revealing the fundamental processes by which dust particles first coalesced 4.5 billion years ago, laying the groundwork for the eventual formation of Earth. The force responsible for binding these aggregates together, the scientists determined, is not gravity. These particles are simply too small for gravity to be an efficient or effective adhesive at this microscopic scale. Instead, the prevailing theory points to an entirely different, yet surprisingly common, force: electrostatic force. This electrostatic attraction, the force that binds these dust aggregates, is the very same phenomenon we encounter in our everyday lives. Think of the familiar experience of pulling clothes from a dryer, how sometimes socks cling stubbornly to shirts, or fabrics adhere to your skin. That clinging sensation is caused by static electricity. It is this identical, subtle electrical effect that allows one microscopic dust particle in the nascent solar system to stick to another. These initial aggregations of dust particles begin to form what we might playfully describe as balls of fluff, cosmic dust bunnies. The tiny static charges they carry allow them to gently adhere when they collide, gradually building up structures reminiscent of the dust bunnies that often accumulate under our beds. Only these are the embryonic seeds of future worlds. These cosmic dust bunnies, initially smaller than the head of a pin, are in fact planets in the making. They represent the first significant step beyond individual dust grains, growing steadily in size as more particles adhere. The dust is now in discernible clumps, but it is still just that, soft, porous balls of dust. To transform these fragile dust balls into solid, resilient rocks requires an entirely new and powerful process, something akin to a cosmic electric storm. Just as clouds here on Earth can accumulate electrical charge, leading to dramatic bolts of lightning, so too can vast clouds of gas and dust in space. It is believed that these powerful electrical discharges, these cosmic lightning bolts, could have smashed through the loosely bound dust balls, heating them to an astonishing 3,000 degrees Fahrenheit in a matter of minutes. This intense, instantaneous heat would have fused the dust particles together, and as they subsequently cooled, they would have solidified into solid rock. Remarkably, meteorites that fall to Earth today often carry within them tangible evidence of this ancient process. Inside these celestial visitors, we sometimes find tiny, spherical globules of rock, known as chondrules. These minute formations are believed to be the very ancient rock balls, the fundamental building blocks, that once formed in the chaotic, electrically charged environment of the early solar system. To form a planet like Earth, these tiny, newly solidified balls of rock had to continue their growth. They had to collide, stick together, and progressively increase in mass. Rocks began to accumulate through a myriad of accidental collisions, a process that, while constant, could have taken a considerable amount of time to reach a significant scale. Eventually, Through countless such impacts, these baby planets, which we refer to as protoplanets, grew to the size of asteroids spanning kilometers across. At this stage, the embryonic Earth, still a young and volatile world, had grown to a size roughly equivalent to a few city blocks. Crucially, it had now reached a critical threshold, a point where a new and immensely powerful force could finally begin to assert its dominance: gravity. Once a protoplanet achieves a certain mass, its gravitational field becomes strong enough to significantly influence other nearby objects. At this pivotal juncture, a single asteroid would gravitationally attract a neighboring asteroid. These two celestial bodies, which might otherwise have simply passed each other in the vastness of space, are now drawn inexorably together by their mutual gravitational pull, leading to a direct collision. Once gravity truly begins to exert its influence, the entire process of planetary accretion accelerates dramatically. Instead of merely passively plowing through scattered material and gradually increasing in size through random impacts, a protoplanet now actively begins to draw in matter from its surroundings. Its growing gravitational field acts like an invisible magnet, pulling in countless rocks and debris, then holding them firmly in place, leading to the rapid accumulation of larger and larger piles of cosmic rubble. This formation process, which previously took an immense amount of time to reach the scale where gravity could effectively kick in, suddenly shifts into overdrive, and the nascent planet begins to grow with astonishing rapidity. However, planets, especially those like Earth, are far more than just overgrown piles of rock. These accumulating rocks, at this stage, are typically lumpy, irregular, and fundamentally inert. The profound question then emerges: how did our Earth, a world that is so distinctly round and so miraculously full of life, evolve from such a chaotic, misshapen amalgamation of rubble? The early solar system, particularly during this tumultuous period of planetary formation, was a truly destructive environment. Dust coalesced to form rocks, and rocks joined to form asteroids. Yet, when we observe asteroids today, most of them bear little resemblance to the perfectly spherical, vibrant Earth we inhabit. Indeed, if you were to observe a close-up image of a typical asteroid, you would see a highly irregular, often distorted shape, perhaps resembling a misshapen peanut or a potato that has been repeatedly battered and scarred. Their surfaces are typically pockmarked with giant craters, and their overall forms are distinctly oblong, far from the smooth spheres we associate with planets. The young Earth, in its earliest stages, was likely just one among billions of these misshapen, irregular space boulders, a cosmic lump of rock and metal. To truly become a planet, to assume its iconic, perfectly spherical form, it had to undergo a profound transformation. This process of becoming round only truly begins when a celestial body reaches a considerable size, typically several hundred miles across. At this critical mass, its own immense internal gravity begins to exert sufficient force to physically alter its shape. Once a celestial body accumulates enough material, enough mass, its gravitational force becomes overwhelmingly strong. Any giant mountains or towering irregularities on its surface will be relentlessly crushed down by the immense, inward pull of its own gravity. The gravitational force is so potent that it can actually cause rocks to deform and break under the immense pressure, effectively causing the rocky material to behave almost like a viscous fluid over vast timescales. This internal plastic deformation, driven by self-gravity, allows the object to gradually settle into the most energetically efficient shape possible, a perfect sphere. Thus, huge outcrops of rock crumble and fall, and the immense self-gravity of the early Earth, exerting its relentless pressure from all directions, eventually crushed its lopsided pile of rubble into that vast, perfectly round ball of rock we recognize. A once misshapen, irregular mass of debris was transformed into a miniature world perfectly spherical in its nascent form. The Earth had acquired its iconic, new shape, but at this point, it was still just a massive, solid ball of rock. However, its internal structure, its very essence, was also destined for a dramatic and profound change. Even as it rounded into shape, the early solar system remained a violent place. Cosmic rocks and boulders continued to rain down from space, a relentless bombardment of impacts. Each of these collisions, whether large or small, imparted immense kinetic energy into the nascent planet, converting that energy into heat, causing the ground to warm considerably. An object moving at high velocity stores an enormous amount of energy. When such an object impacts the Earth, all that kinetic energy is suddenly and violently dumped into the planet's material, causing it to heat up, to melt, and to transform. Consequently, the early Earth became a seething, molten mass, and it remained in this fiery, liquid state for an extended period. Imagine, if you will, the Earth not as a solid sphere, but as a vast, churning ocean of molten rock, much like the incandescent, glowing metal within a blast furnace, such as those found at the Severstall plant in Detroit. Believe it or not, this incredibly destructive and fiery process, this period of intense planetary melting, was absolutely fundamental and ultimately made life on Earth possible. In such furnaces, ground-up iron ore, a complex mixture of rock and metal, much like the raw materials of the early Earth, is fed in. The intense heat of the furnace melts everything, transforming the solid ore into a glowing, liquid state. This molten iron, flowing like a river of fire, reaches temperatures of around 700 degrees Fahrenheit, a temperature remarkably close to what the surface of our Earth would have been like 4.5 billion years ago. Picture an entire planet, not just a furnace, but an entire world in this molten state. In the distance, you would have witnessed colossal, thundering volcanoes, continuously spewing out incandescent rivers of lava, painting a scene that could easily have been ripped from the fiery pages of Dante's Inferno. In this liquid, superheated environment, a crucial process began to unfold. Iron, being significantly denser and heavier than rock, began to separate from the lighter rocky minerals. This fundamental separation, driven by density, allowed the lighter molten rock to rise towards the surface, where it would eventually cool and solidify, forming the Earth's nascent crust, the very ground we walk upon today. Simultaneously, the heavier molten iron began its inexorable descent, sinking downwards, deeper and deeper, until it reached the very center of the planet, forming Earth's molten core. This process, a grand-scale planetary differentiation, was nothing short of amazing to witness, even in simulation. We are, in effect, observing the very mechanism that crafted the foundational crust of the Earth billions of years ago. The solid surface that supports all life, and on which we stand every single day. While the rocky surface is undeniably where we live, where all the complex tapestries of life unfold, it is without Earth's dynamic, molten iron core that none of us could possibly survive. This crucial separation of iron from the rocky minerals, a direct consequence of the planet's molten phase, was the vital precursor to another life-sustaining phenomenon. As the molten iron descended, and then swirled within the Earth's center, its convective motion eventually generated a powerful magnetic field that envelopes our planet. And, in a very real sense, that magnetic field is a fundamental reason why we are here today. This swirling, molten iron within Earth's core acts like a colossal, planetary dynamo, generating a vast and powerful magnetic field that extends far out into space, forming an invisible shield around our world. This magnetic field serves as a crucial cosmic protector, deflecting deadly radiation from the sun and other cosmic sources, safeguarding the delicate conditions necessary for life on the surface. However, at this early stage, the young Earth was still a relatively small world, far smaller even than our moon is today. This newly formed, magnetically shielded world still had a considerable amount of growing to do. It needed to accumulate significantly more mass to become the planet we know. And, perhaps even more critically, it had to navigate a perilous cosmic environment, avoiding the constant threat of being utterly blown to pieces. Thousands upon thousands of other protoplanets, celestial bodies of varying sizes, were still hurtling around the young solar system, and many of them were on direct collision courses with the nascent Earth. A mere 100,000 years had passed since the initial formation of our solar system, a blink of an eye in cosmic terms. Yet, the young Earth was already beginning to resemble a planet in its own right. It had taken on a spherical shape, possessed a distinct iron core, and was developing a nascent rocky surface. Despite these significant advancements, our baby planet was still only a few hundred miles across, a mere fraction of its ultimate size. It had an immensely long journey ahead, needing to grow approximately 4,000 times more massive to reach its current proportions. And it wasn't alone in this cosmic growth spurt. It faced intense competition. Thousands of other protoplanets, ranging in size and trajectory, were still shooting through the chaotic early solar system, often colliding with each other at staggering speeds, exceeding 20,000 miles per hour. Tangible proof of this ancient, incredibly destructive era can still be found today, etched into the landscape of modern-day Arizona. We're not talking about the famous meteor crater itself, which is a relatively recent impact, only about 50,000 years old. Rather, the evidence lies within the very asteroid that gouged out that immense crater. An asteroid whose origins stretch back an astonishing 4.5 billion years to the tumultuous period of planetary formation. Researchers like Mark Sykes and Marvin Kilgore are convinced that this ancient asteroid was a remnant from one of those incredibly violent events in the early solar system. This particular asteroid had journeyed through the cold, dark expanse of space for billions of years before its ultimate, fiery impact with Earth. Their mission is to locate a fragment of this original asteroid, a precious remnant from that chaotic, formative period of planetary development. Approximately 6 miles from the well-known meteor crater, which was formed by an impact some 50,000 years ago and scattered countless fragments across the landscape, they search. Sykes and Kilgore are convinced that the original asteroid was rich in iron, a telltale sign of its origin deep within a shattered protoplanet. Armed with this knowledge, they have come prepared with an impressive array of specialized metal detectors, hoping to unearth a piece of this ancient cosmic traveler. As they test their equipment, the detector emits a distinct, high-pitched whine. "Oh yeah, that's the sound we're listening for." A hopeful sign. But even with a sophisticated, quad-drawn metal detector, finding meteorites, especially those buried for eons, proves to be an incredibly challenging task. "Are you pretty convinced there's nothing there?" one asks, as the detector remains silent over a particular spot. "I don't really. Not detecting anything," comes the reply. They find plenty of buried metal, but it's invariably modern debris, old bolts, pieces of wire, human detritus. "My great discovery of the afternoon has been this bolt and this piece of wire," someone laments, highlighting the difficulty. Hours of searching pass, punctuated by many false alarms and growing frustration. Then, as the light begins to fade and the day draws to a close, the detector suddenly sounds again, a clear, unmistakable signal. How about that? Success at last. The meteorite they finally unearth is a remarkable specimen, composed of over 90% iron and nickel. Such a composition could only have formed deep within the core of a protoplanet. A body large enough to differentiate, with heavy metals sinking to its center. This discovery provides compelling evidence that the protoplanet from which it originated must have been violently smashed apart in a brutal, cataclysmic collision. As one scientist explains, Well, in the early solar system, it was a pretty violent place, and these protoplanetary embryos would smash into each other. And they would shatter each other, exposing the interior cores like this. It was a very tumultuous time. Entire nascent worlds, nascent planetary bodies, were reduced to mere chunks of rock and metal, scattered across the vast emptiness of outer space, their potential for life forever extinguished. In the early solar system, these vast, destructive collisions were not isolated incidents. They were commonplace, a defining feature of that chaotic era. The young Earth, still in its formative stages, was constantly in grave danger, perpetually threatened by these titanic impacts. This period of intense planetary bombardment and gravitational warfare is aptly named the Titanomachy, a term derived from ancient Greek mythology, literally meaning the War of the Titans. All rocky planets, including our own Earth, had to endure and survive this immensely destructive phase. Sometimes, these nascent worlds would shatter completely, their material dispersed into the void. In other instances, one protoplanet would gravitationally dominate and effectively consume another, incorporating its mass into its own growing bulk. All the big guys are sort of competing with one another in a very violent way. Actually, to see who comes out on top by eating all their neighbors. One astrophysicist vividly describes, this brutal, cosmic battle for dominance raged on for an astonishing period, lasting over 30 million years. Finally, after millions of years of relentless collisions and gravitational accretion, the thousands of smaller protoplanets that once populated the inner solar system had largely combined into a select few full-size planets. These were the nascent versions of Mercury, Venus, Earth, Mars, and a fifth, tragically fated planet named Theia. And Theia, a formidable body, was racing on a collision course directly toward Earth. Our planet's last, and arguably most significant, giant impact. Theia was an immense celestial body, roughly the size of Mars, making it large enough to utterly destroy the nascent Earth. Had this colossal object struck our planet head-on, the consequences would have been catastrophic beyond imagination. As one scientist grimly notes, if that thing had hit us straight on, it could have literally blown the Earth to bits, and then we wouldn't even have a planet today. Indeed, if this Mars-like object had delivered a direct, full-force blow to Earth, it's entirely plausible that our planet would have been annihilated, leaving behind nothing but another vast asteroid belt where Earth currently orbits the Sun. But, in a stroke of incredible cosmic fortune, Earth was spared such a complete obliteration. Instead of a catastrophic head-on collision, Theia delivered a glancing blow, a powerful but indirect impact. Even so, this event remains the single most violent cataclysm our Earth has ever known. The sheer energy unleashed by this impact transformed our planet back into a seething, incandescent world, a vast, global ocean of magma stretching to depths of 600 miles. Our nascent Earth, against all odds, barely survived this monumental encounter, but it was irrevocably changed, its very essence altered forever by the immense forces at play. The impact was so profound that it blasted an unfathomable amount of material out into the cold vacuum of space. Imagine a mountain range, not just a few peaks, but a continuous chain as wide as the entire continent of America, soaring to an impossible height of 10,000 miles. That's the sheer scale of the rock and debris that was ejected from Earth's surface and into its immediate orbital vicinity. The force, the catastrophic violence, was truly beyond comprehension, sending colossal quantities of superheated material swirling around our scarred planet. This vast cloud of ejected debris didn't simply dissipate into the void. Instead, under the relentless pull of gravity, it began to coalesce, forming a colossal, shimmering ring of rock and molten material around the battered Earth. Over time, within this luminous, swirling ring, the material gathered into not one, but two distinct rocky bodies both locked in orbit around our planet. The prevailing scientific theory now suggests that the Mars-sized object, Theia, striking Earth approximately 4 billion years ago, threw off so much material that it likely formed not just a single moon, but initially, a pair of celestial companions. For millions upon millions of years, the Earth's night sky would have been dominated by the majestic presence of two moons, each a silent sentinel in the cosmic darkness. But even these two cosmic companions were not destined to remain separate. Gradually, inexorably, their orbits brought them closer and closer, until, in a final, gentle collision, they drifted together and merged. This cosmic embrace resulted in the formation of the single, massive moon that graces our skies today, a familiar, luminous orb that has captivated humanity throughout history. Our moon, in its current form, is a truly exceptional celestial body. There is no other planet in our solar system that we know of which possesses a moon as disproportionately large in comparison to its parent planet's size. Indeed, the Earth and its moon are almost like a binary planet system, two worlds locked in a gravitational dance, circling each other through the cosmic ballot. And without this colossal moon, it is a chilling possibility that we, life on Earth, might not even be here. The moon plays an absolutely pivotal role in the very survival of life on Earth, a silent guardian in the vastness of space. The fundamental reason lies in its profound gravitational influence. As the moon orbits our planet, it acts like a colossal gyroscope, stabilizing Earth's axial tilt. This constant, steadying force ensures that Earth continues to spin at a relatively consistent angle relative to its orbit around the Sun. This stability is directly responsible for the predictable and regular seasons we experience. Seasons that are not too extreme, but rather consistent patterns that life, in all its forms, has been able to depend upon as it evolved over billions of years. Imagine a world where the axial tilt wildly fluctuated, climates would swing dramatically, rendering sustained life almost impossible. Thanks to this celestial dance, Earth maintains a remarkably stable temperature, a delicate balance where it is neither searingly hot nor impossibly cold. This perfect thermal equilibrium is a direct consequence of our planet's optimal distance from the Sun, placing us squarely within the Goldilocks zone, combined with the profound stabilizing influence of our massive moon. The result is a planet not perpetually covered in vast sheets of ice, nor shrouded in a suffocating shroud of steam, but rather a world blessed with an abundance of liquid water, the very elixir of life. Yet, this essential water, so ubiquitous across our planet's surface, must have originated somewhere. The newly formed Earth, in the aftermath of the Theia impact and its subsequent cooling, was a predominantly dry world, a barren landscape devoid of the vast oceans we now cherish. To acquire the life-giving liquid that defines our planet, Earth once again had to face a cosmic disaster, a tumultuous event that would fundamentally alter its composition. It had now been approximately 500 million years since the Sun first ignited, its nuclear fires blazing steadily. Fast forward 4 billion years from this point, and the first humans would finally set foot on this extraordinary world. But at this ancient juncture, with the moon having just formed, the Earth was still a largely desolate and arid landscape. One of the more astonishing, yet widely accepted, ideas in modern astronomy posits that Earth began its existence as a hot, parched world, entirely devoid of indigenous water. As the planets of our solar system were forming, the Sun's intense radiation, its powerful stellar winds, effectively vaporized any water molecules present in the inner regions of the solar system. Closer to the Sun, temperatures were simply too high for water to condense and persist in liquid or solid form. However, farther out, beyond the snow line, where temperatures were significantly cooler, ice and water vapor were able to collect and freeze, forming vast reserves on comets and icy asteroids. Meanwhile, closer to the Sun, the young Earth remained stubbornly dry. So, the profound question arises, how did things change? How did our planet, initially so parched, come to possess its magnificent, life-sustaining water cycle? The scientific consensus points to an external origin. The water, it seems, must have arrived from somewhere else. If you are to construct a solar system rich in water, you must find a mechanism to transport that water from its frozen reservoirs in the outer reaches, where it could survive the sun's heat, into the warmer, inner parts where rocky planets like Earth reside. And the most compelling candidates for this cosmic delivery service are comets and asteroids. These celestial wanderers, originating from the colder, outer solar system, contain immense reserves of water, locked away as ice within their rocky and dusty matrices. However, at this early stage, these comets and icy asteroids were still hundreds of millions of miles distant from the young Earth, their precious cargo seemingly out of reach. Then, something momentous shifted. An extraordinary event, a cosmic upheaval, occurred that effectively tossed these distant asteroids and comets right across the entire solar system. This was not a gentle, gradual process. It was a period of immense gravitational instability, a cosmic roller coaster ride for the gas giants themselves: Jupiter, Saturn, Neptune, and Uranus. This wasn't an event that unfolded in the absolute infancy of the solar system, but rather, as one scientist vividly describes it, more like its teenage breakout years, a period when the planets just started the party for a while. At this stage, the young gas giant planets had not yet settled into the stable, predictable orbits we observe today. As their immense gravitational fields interacted, their orbits began to shift and migrate. Jupiter and Saturn, in particular, fell into an intricate and powerful gravitational dance. Every time Saturn completed one orbit around the Sun, Jupiter would complete exactly two, bringing them into a precise, repeating alignment at the same spot in their respective paths. This consistent alignment meant that their colossal gravitational forces tugged on each other in the same direction, repeatedly. This repeated gravitational perturbation first destabilized their own orbits, and then, like a chain reaction, the entire outer solar system was thrown into chaos. The whole thing just goes crazy, a scientist explains. The analogy often used to describe this planetary pandemonium is that of a bowling ball striking pins. It just goes bam all over the place. That's what this would have looked like. Neptune and Uranus, under these immense gravitational stresses, literally switched places in their orbits, migrating to new positions. Saturn, responding to Jupiter's influence, raced outwards, farther from the Sun. This gravitational reshuffling of the giant planets had a profound and widespread consequence. It scattered billions upon billions of asteroids and comets from their stable, distant orbits, sending them careening onto new, highly eccentric paths. And a significant number of these cosmic projectiles were now headed directly for the inner solar system, many on a collision course with Earth. These scattered asteroids and comets, flung across the solar system, bombarded the inner planets with relentless fury, some of them hitting the Earth and Moon, a scientist confirms. It was a period of intense, sustained cosmic violence, so severe that we believe that every square inch of the Earth got hit by a comet or an asteroid during this period. It would have been an incredibly hostile environment, not a fun time to be here, to say the least. This relentless bombardment, aptly named the Late Heavy Bombardment, lasted for hundreds of millions of years, an epoch of constant impacts and destruction. It only subsided once the gas giants, after their chaotic gravitational dance, finally settled into the stable, predictable orbits that we observe today, restoring a semblance of order to the solar system. But the Earth itself had been fundamentally and irrevocably changed by this cataclysmic period. Those incoming comets and asteroids were not merely composed of rock. Crucially, many of them were rich in ice, frozen water. Comets, in particular, are famously described as dirty snowballs from space, vast reservoirs of ice, dust, and rocky material. Even many asteroids, once thought to be purely rocky, have been found to contain significant amounts of water ice. Thus, it was this cosmic hailstorm, this seemingly destructive period of bombardment, that delivered the immense quantities of water necessary to fill our planet's oceans. So, the next time you pour yourself a refreshing glass of water, take a moment to consider its astonishing cosmic origin, realizing that you're probably drinking comet and asteroid juice. The arrival of this abundant liquid water was the final, indispensable step in creating a truly habitable planet. A remarkable sequence of catastrophes and cataclysms, from the supernova that triggered our solar system's birth, to the moon, forming impact, and finally, to this watery bombardment, had paradoxically conspired to create a world that was absolutely perfect for life. But this brings us back to that monumental question: has this incredible, improbable chain of events occurred elsewhere among the countless stars? Or, in this vast, silent universe, are we truly alone? How did we get here? Planet Earth exists today only because of an extraordinary, unlikely chain of cosmic events, a lucky throw of truly cosmic dice. 5 billion years ago, looking at the raw, chaotic materials, the odds would have seemed impossibly slim that a planet precisely like Earth would form within a rather unremarkable arm of the sprawling Milky Way galaxy. It's an analogy akin to trying to throw two sixes with a pair of dice that each possess thousands of sides, an almost insurmountable statistical challenge. We know, with absolute certainty, that it happened once, for otherwise we would not be here to contemplate it. But what, then, are the odds that this cosmic jackpot has been won elsewhere, that other planets, orbiting other stars, also harbor life? Life, at least as we understand it, requires a planet with a very specific set of attributes, the right temperature range, a suitable size, a stabilizing moon, a protective magnetic field, and, crucially, just the right amount of liquid water. The conditions, it seems, must be absolutely perfect, a delicate balance of innumerable factors. Yet, astonishingly, despite the apparent rarity of these conditions, there may be countless Earth-like planets scattered across the universe, patiently waiting to be discovered. And thanks to the sheer, mind-boggling scale of the cosmos, the probability dictates that we may indeed find one any day now, particularly with the incredible capabilities of instruments like the Kepler Space Telescope. Jeff Marcy, a mission co-investigator for Kepler, describes its singular, profound objective. It has only one goal, and that's to discover Earth-sized planets around other stars that you see in the night sky. Prior to Kepler's launch, Earth-sized planets were incredibly difficult to spot. Astronomers, using earlier methods, took over 20 years to discover approximately 500 exoplanets, most of which were gas giants, hundreds of times larger than Earth. Since the advent of Kepler, that number has literally exploded. Kepler has already identified a couple of thousand planet candidates, many of them existing within multi-planet systems. 2, 3, 4, 5, and even 6 planets all orbiting the same star. So we're finding an absolute avalanche of planets out there among the stars, a testament to the telescope's revolutionary capabilities. Kepler has even found one planet that is only twice the size of Earth and situated within the habitable zone of its star, meaning it's at the right temperature for liquid water to potentially exist on its surface. While we don't yet know if this particular planet possesses other Earth-like attributes, such as a substantial atmosphere or liquid water, the sheer volume of discoveries suggests that even if it doesn't, there are many more planets out there, and Kepler has only surveyed a minuscule fraction of the sky. It's not even looking at the whole sky, It's looking at a very tiny slice of stars in the galaxy. And in fact, if you were to look up, you could cover it with just your thumb. Consider the immense scale of our own galaxy, the Milky Way, which contains an estimated 200 billion stars. Based on the groundbreaking data from Kepler and other ongoing searches, it is now widely believed that a significant proportion of these stars, perhaps something like half of them, or even more, harbor planets. This staggering implication means that at least 100 billion planets have formed within our Milky Way alone. While truly Earth-like worlds, with all the precise conditions for life, may indeed be rare, it seems a very safe bet that they are out there somewhere amidst this astronomical abundance. The odds of getting one Earth-like planet, if you consider a single star, are indeed extremely small, much smaller than, say, rolling a double six in a game of craps. But, as the saying goes, if you have enough dice, you are eventually guaranteed to roll sixes. And if you have a colossal number of planets, as our galaxy appears to, then you are virtually guaranteed to find Earths. With so many planets estimated to exist within our own galaxy alone, even if the chances of one being truly Earth-like are as slim as 1 in a million, there should still be thousands of such worlds. And when we consider the universe at large, which contains hundreds of billions of galaxies, each more or less comparable to our Milky Way, the total number of planets becomes virtually uncountable. The statistical certainty, therefore, suggests that alien Earths must be everywhere. While we haven't yet definitively discovered even one other planet confirmed to host life, statistically speaking, it is a rock-solid certainty that millions, if not billions, of planets like Earth exist out there. And with such an astronomical number of Earth-like planets, it seems almost inevitable that some of them must surely possess intelligent life. One prominent astrophysicist declares, "I would bet everything, I would bet my house, that there is another Earth out there somewhere." It's a compelling thought, a testament to the power of numbers on a cosmic scale. Planet Earth, a shimmering jewel in the profound darkness of space, our home, is a world of timeless beauty, yet it is also a place shaped by incredibly violent, dynamic forces. Volcanoes, for instance, represent one of the most powerful and awe-inspiring natural phenomena on our planet. They are both creators and destroyers, constantly forging new land from the Earth's fiery depths, while simultaneously obliterating the old. They blast out vast quantities of gases, profoundly transforming the very air we breathe. Deep within our planet's oceans, far from the sun's light, volcanic heat fuels strange and wondrous new forms of life, thriving in environments that would otherwise be utterly barren. Volcanoes, in essence, help to power the living Earth, acting as crucial engines of geological and biological activity. And it is precisely this connection between volcanoes and life that now guides our search for signs of life on alien worlds. We understand that life, as we know it, requires liquid water, and it also needs a source of energy. This is precisely where volcanoes enter the cosmic equation. They pump out immense amounts of geothermal energy. Therefore, the hypothesis is compelling. If we can find evidence of active volcanoes on other worlds, we might just find life. The initial focus of this profound search begins relatively close to home, on the planet orbiting closest to Earth, Venus, a world that, at first glance, appears remarkably similar to our own. Venus and Earth share striking resemblances. They are roughly the same mass, and they orbit at a similar distance from the Sun. In many ways, they are like cosmic twins. Indeed, 3 billion years ago, Earth and Venus were likely very similar worlds, both possessed nascent landmasses, potentially vast oceans, and developing atmospheres. Both planets, at that incredibly ancient time, seemed to be perfectly poised for the emergence of life. But somewhere along their parallel journeys, something went terribly wrong on Venus. Something caused Venus to diverge radically from Earth's life. Sustaining history, Venus, it seems, took a definitive turn to the dark side, a very long time ago. Today, Venus is nothing short of a hellhole, a stark and terrifying contrast to our vibrant home, truly our evil twin. Its surface temperatures are scorching, reaching a blistering 900 degrees Fahrenheit. Hot enough, in fact, to melt certain metals. There, a human would stand absolutely no chance of survival. Venus is a classic example of a runaway greenhouse world. Its incredibly dense atmosphere is thick with carbon dioxide, which acts like a suffocating blanket, trapping heat from the sun with devastating efficiency. Actual images of Venus's surface, obtained through radar, reveal a barren, superheated wasteland utterly inhospitable. This suffocating, thick blanket of carbon dioxide is what ultimately killed Venus, transforming it into an inferno. And the primary source of all that carbon dioxide, scientists discovered, was volcanoes. Orbiting space probes provided the first crucial clues. Radar signals, capable of punching through Venus's impenetrable, thick clouds, revealed a landscape scarred by countless volcanic formations, strikingly similar to geological features we observe right here on Earth. Specifically, the vast shield volcanoes of Hawaii. Shield volcanoes, with their characteristic round, flat shapes, are known for their effusive, long-lasting eruptions, oozing lava for thousands of years, gradually building up their immense structures. Once scientists were able to comprehensively map the entire surface of Venus using cloud-penetrating radar, they began to meticulously study the landforms etched into its surface. What they saw was remarkably familiar. In particular, they identified giant shield volcanoes, astonishingly similar in form and scale to the iconic shield volcanoes found in Hawaii. The radar images of Venus were, as one expert put it, dead ringers for the Hawaiian formations. For the first time, a clear picture of Venus's true nature was revealed, and the scientific community was genuinely shocked. They found a surface deeply scarred, undeniably volcanic. Estimates suggest there are at least 1,000 very large volcanoes, and potentially tens or even hundreds of thousands of smaller ones, scattered across the Venusian landscape. A staggering 3/4 of Venus's surface is covered by vast lava plains, an undeniable testament to an ancient, planet-wide cataclysm of volcanic activity. This was a world that, billions of years ago, could have been a hospitable home for life. Instead, it was tragically engulfed by fire. The volcanoes on Venus belched trillions of tons of carbon dioxide into its atmosphere, relentlessly thickening the insulating blanket. As the CO2 accumulated, temperatures soared to unimaginable levels, causing any nascent seas or oceans to boil away into steam, irrevocably drying out the planet. This initiated a runaway greenhouse process, a vicious cycle that spiraled out of control. On Earth, carbon dioxide is naturally absorbed and sequestered by rocks, through weathering processes, and dissolved into our vast oceans, helping to regulate our climate. But on Venus, with no surface water to absorb it, and with temperatures now so extreme, the carbon dioxide could not even effectively combine with the silicate rocks. As carbon dioxide was continuously released into the atmosphere by volcanic activity over immense geological timescales, there was progressively less and less of a natural mechanism to remove it from the atmosphere. If Venus ever did harbor life, this catastrophic volcanic activity and the ensuing runaway greenhouse effect would have utterly sterilized the entire world, wiping out any potential for biological existence. Consequently, Earth remains the only living world we definitively know of in our solar system. However, this profound understanding, this singular status, may be poised to change. Consider the gas giant Jupiter, a colossal world of swirling clouds and immense gravity. Its moons, at first glance, appear frozen and utterly dead, or so we once thought. But if we look closer, a profound mystery begins to emerge: a strange, enigmatic cloud hanging over a seemingly cold and lifeless world. On Venus, the discovery of volcanoes transforming an Earth-like world into a superheated hell was, in hindsight, perhaps not entirely surprising. But spotting active volcanoes on a moon, a small, distant satellite, was an absolute shock, a revelation that expanded our understanding of planetary dynamics. In March 1979, the Voyager 1 space probe made its historic first close-up pass of Io, Jupiter's tiny, innermost moon. It was a world that astronomers had previously considered cold, geologically inert, and utterly uninteresting. Yet, what Voyager 1 observed was truly bizarre. They saw this arc next to the moon, and it looked almost as if there was another moon behind it. A puzzled scientist recalls, "The initial reaction was one of confusion and disbelief. Everybody knows that Io is dead, boring, uninteresting," was the prevailing sentiment. And then, the astounding realization dawned. Oh my God, it's a volcanic eruption. Voyager 1 revealed a moon absolutely covered with volcanoes, a world of intense geological activity, with eruptions occurring constantly. What these volcanoes were spewing out was primarily sulfur, and a lot of it. Sulfur, as it changes temperature, dramatically shifts its color. It can be brilliant red, vivid orange, bright yellow, or deep black. Consequently, the images of Io's surface made it appear like a pizza covered with different kinds of cheese and olives where the little black spots are. It was not dead, it was violently alive and kicking. This tiny moon possesses over 400 active volcanoes, making it the most volcanically active body in the entire solar system. Its largest, named Pell, erupts from a gigantic lava lake, sending plumes of material soaring nearly 250 miles into space. If we could stand on the edge of that lava lake and watch that plume shooting off into the blackness of space, that would be an incredible sight. One imagines, Pell's eruptions are so immense precisely because Io is so small. With virtually no atmosphere to contain the gases and very little gravity to pull the material back down, there's nothing to hold the lava, or the ejected plumes, back. These vast, spectacular eruptions make even Earth's most powerful volcanoes look like mere firecrackers in comparison. But how can such a tiny moon, so far from the sun's direct heat, be so incredibly volcanic? The astonishing answer lies with its colossal parent planet Jupiter. Just as our own moon exerts a gravitational pull that raises tides in Earth's oceans, Jupiter's immense gravity raises tides on Io. Not tides of water, but tides of solid rock. Io's orbit around Jupiter is not a perfect circle, it's elliptical, meaning sometimes it's closer to the gas giant, and sometimes it's farther away. This constantly changing distance means that Jupiter delivers a relentless, gravitational pounding to Io. As Jupiter's gravity pulls on Io, it stretches the moon a little bit harder when it's closer, and a little bit weaker when it's farther away. This continuous stretching and squeezing causes the moon to deform, to literally flex and bulge. This phenomenon is known as a tidal force. While the moon doesn't visibly stretch to a dramatic extent, the deformation, though subtle, is enough to generate immense internal heat. It's the same principle of friction we experience when we rub our hands together rapidly. The friction creates warmth. Jupiter's immense gravity stretches and squeezes Io with every 2-day orbit, causing the ground to rise and fall by an astonishing nearly 300 feet. This constant, internal pummeling generates intense heat and immense pressure within Io's interior. Wherever there's a weak point or fissure in Io's crust, the superheated lava, driven by this immense pressure, rushes out, manifesting as volcanic eruptions. The volcanism on Io is not localized to specific areas, as it often is on Earth along plate boundaries or weak spots in the crust. Instead, this is an entire moon that's one active hotspot, a world completely defined by its volcanic activity. Thanks to the incredible, relentless power of Jupiter's gravity, Io holds the distinction of being the most volcanically active world in our entire solar system. The discovery of Io's intense volcanism taught us something profoundly new and unexpected about the mechanisms that drive geological activity in the cosmos. It demonstrated that internal sources of energy, beyond residual heat from formation or direct stellar radiation, can indeed power volcanism in ways fundamentally different from what we observe on Earth. In the frigid depths of outer space, tidal forces, the differential squeezing and stretching exerted by the immense gravity of a gas giant on its moons, can generate enough internal friction and heat to create widespread volcanic activity. This was a true game changer in our understanding of planetary science. Io is undeniably a lava world, superheated and violently dynamic. It's incredibly challenging to imagine anything surviving in such an extreme environment. Yet, the underlying volcanic principle at play here is fundamentally the same as on Earth: pressurized, superheated magmas, or in Io's case, sulfurous rock beneath the surface blasts through fissures and weak spots in the crust. But not all volcanoes require molten magma, strikingly. They don't even need to be hot. Let us journey farther out, past Jupiter and its fiery moon Io, into the outer reaches of our solar system, where the cold becomes truly profound. Here, the distant moon Triton, orbiting the ice giant Neptune, is so incredibly cold that much of its tenuous atmosphere actually freezes solid, raining down as nitrogen ice. Yet, even in this unimaginably frigid environment, there are active volcanoes that might just hold a tantalizing secret, a clue to the potential for alien life. When we typically think of volcanoes, we envision towering mountains of solid rock, beneath which immensely hot, pressurized molten rock violently erupts as incandescent lava. But as we've learned, not all volcanoes operate this way. On other worlds, there exist entirely different types of volcanoes that do not utilize molten rock at all. Triton, nestled at the very frontiers of the Sun's planetary system, orbits the distant ice giant Neptune, an astonishing 2.5 billion miles from the Sun. The ambient temperature here is a frigid 390 degrees below zero Fahrenheit, a cold that borders on the absolute. When NASA's Voyager probe flew past Triton, it unveiled a world predominantly covered with frozen nitrogen ice. But the probe discovered something else, something utterly unexpected for such a cold, distant body. As Voyager flew by, it saw these black smudges, and all the smudges were going in one direction, almost as if there was a wind blowing dark material dust in one direction. Unmistakable signs of active geological processes on a world so cold it freezes nitrogen solid. These were volcanoes erupting at nearly 400 degrees below zero, temperatures where molten rock is utterly impossible. Instead, Triton was spewing out a mixture of nitrogen gas and fine moon dust. These geysers, as they were recognized, eject not only liquid nitrogen, which briefly becomes fluid before freezing, but also lighter, dusty material that can be carried even farther by the moon's weak winds. So you have this wonderful sort of double plume of an icy area and then a darker smudgy area, basically made of dust like moon dust. A scientist explains. Triton's surface is a vast expanse of nitrogen ice, but beneath this frozen crust, scientists believe there are subsurface lakes of liquid nitrogen. How can this be, in such extreme cold? The explanation lies in a peculiar property of nitrogen ice. It allows light to penetrate, but effectively traps heat, creating a kind of greenhouse effect. There's almost a bit of a greenhouse effect going on Triton, a researcher notes, explaining that a transparent layer of nitrogen ice acts much like the glass in a greenhouse here on Earth. Sunlight can pass through it, warming the nitrogen beneath, but the resulting heat is then trapped by the overlying ice. Just a few degrees of warming are all it takes to transform nitrogen ice into gas, creating a crucial temperature gradient. This change in temperature is precisely what's important. and it's enough to melt the nitrogen beneath Triton's surface, causing it to burst through as a geyser. This is a cryovolcano, a cold volcano, so frigid that the material it erupts would instantly freeze water as hard as rock. The discovery of such phenomena has profoundly reshaped our understanding of the solar system, revealing it to be far more active and dynamically diverse than we ever imagined. We have found weird and wonderful eruptions on many planets and moons. But, until recently, the only world where volcanic activity was definitively linked to life was our own Earth. Or so we thought. Now, let us turn our attention to Europa, another of Jupiter's remarkable moons. Europa orbits the gas giant nearly 500 million miles from the Sun, presenting itself as a frozen, 2,000-mile-wide ball of rock, hard ice. From a distance, its surface appears remarkably smooth, almost pristine. But a closer look, through the eyes of orbiting spacecraft, reveals a dramatically different story. Just like its fiery neighbor Europa is subjected to an intense gravitational pounding from Jupiter's enormous mass. This immense tidal force causes Europa's icy surface to heave and flex, creating a complex network of intricate ridges and deep, winding crevices. When we first received close-up images of Jupiter's moon Europa, they looked a little familiar. One scientist recounts, noting that, it turns out it looks like ice floes that you see when you fly over the Arctic, and it turns out it's the same thing. Beneath Europa's several-mile, thick shell of surface ice, scientists now believe there lies a global, liquid ocean. Magnetic readings, in particular, strongly suggest that Europa harbors a subsurface ocean that is a staggering 60 miles deep. Jupiter's relentless gravitational squeezing doesn't just flex the ice, it also heats Europa's rocky core, melting the ice above it. It's not unreasonable to think that as the core is being stretched by tides and heated up, possibly even molten, there's some boundary between a hot core and a liquid water ocean, a researcher explains. And on Earth, where underwater volcanic vents, known as hydrothermal vents, are surrounded by incredibly diverse and thriving ecosystems, the same life-sustaining processes could potentially be occurring on Europa. Here, beneath miles of ice, the darkness would be total, unbroken by any sunlight. The pressure would be crushing, reaching an astonishing 2,000 Earth atmospheres, a truly brutal environment by human standards. Yet, this brutal world could very well be a cradle for life. If life got off the ground here on Earth, why not on Europa? Is the compelling question posed by scientists. All the essential ingredients appear to be present: an energy source, the geothermal heat from the core, volcanic activity, potentially hydrothermal vents, a universal solvent, liquid-watered, and a rich hydrocarbon chemistry, likely delivered by comets and asteroids. Why have this mixing bowl of ingredients that happened on the Earth 3.5 billion years ago, and we have similar conditions on Europa? One points out, so some people are saying if it happened here, why not there? Life on Europa, if it exists, would undoubtedly be incredibly resilient and adapted to extreme conditions, but it is far from impossible. On Earth, we have discovered life thriving at every extreme imaginable in searing heat, under crushing pressures, and in total darkness. Alien life on Europa might, surprisingly, bear some resemblances to Earth life, albeit with extreme adaptations. If life exists under Europa's ice cover, it would almost certainly be aquatic, but without eyes, as there would be no light whatsoever. Such organisms would likely utilize sonar or other sensory systems to navigate their surroundings, literally feeding off the chemical energy provided by volcanic or hydrothermal activity on Europa's ocean floor. Volcanoes, therefore, could be the very source, the genesis of new life. It's even plausible that Europa, with its subsurface ocean, represents a more common template for life, bearing worlds in the universe, and that Earth, with its exposed surface oceans, might actually be the exception. Think of it. Europa could be a template for billions of moons out there that have liquid oceans on them. A scientist muses. So all of a sudden our horizons have expanded several billion times by looking at the moons of Jupiter. This realization is truly a shock. Our solar system alone boasts over 170 moons. Multiply that across the entire universe, and that's an almost unfathomable number of potential places where life might take hold. All it seemingly requires is the presence of liquid water and a source of energy. Potentially, volcanoes provide both, and they, it turns out, are everywhere. Now, let us turn our gaze to Saturn, a gas giant twice as far from the Sun as Jupiter, a world of majestic rings. Yet, even here, in this more distant, colder realm, Saturn too possesses volcanic moons. And, just like Jupiter's Europa, these distant satellites could potentially harbor life, defying the extreme conditions of their environment. Among Saturn's vast retinue of moons, one stands out as truly one of the strangest worlds in our solar system, Enceladus, a small, highly reflective icy body. Saturn itself is a breathtaking spectacle, with a ring system stretching an astounding 600,000 miles wide and an amazing total of 62 moons. But it is Enceladus, one of Saturn's smaller, more distant moons, that holds a profound secret. For a long time, Enceladus was known to be covered in ice, appearing incredibly bright and reflective. But when the Cassini spacecraft made its close flybys, it discovered something truly amazing, not on Saturn itself, but erupting from this seemingly unassuming moon. Backlit by the distant sun, Cassini captured images of a gigantic plume bursting out into space from Enceladus's south pole, an unmistakable sign of volcanic activity, albeit of a very different kind. This was an astonishing discovery, and it immediately helped to answer a question that had puzzled scientists for decades: the enduring mystery of Saturn's E-ring. Saturn's outermost ring, the E-ring, is an immense structure almost 200,000 miles across. For years, its very existence was a paradox. The tiny ice particles that comprise the majority of this ring are simply too far from Saturn's gravitational embrace to remain in a stable orbit indefinitely. They should constantly drift away into the vastness of space. Therefore, something had to be continuously replenishing the ring with new material. The answer, it turned out, lay with the ice volcanoes of Enceladus. Those plumes, observed majestically erupting from Enceladus's south pole, were not simply escaping into space. They're feeding a ring around Saturn, the E-ring, a scientist confirms. So this little moon is giving something back to its parent planet. Water, in the form of vapor and ice, blasts from Enceladus's cryovolcanoes. Upon encountering the near-perfect vacuum of space, this water instantly freezes into countless tiny ice crystals, which then disperse and become the vast, diffuse E-ring of Saturn. One cosmic mystery solved, only to be replaced by another. What precisely creates these powerful volcanic plumes on such a small, icy moon? Cassini's cameras, zooming in with incredible precision on Enceladus's south pole, captured images of huge, tiger, stripe-like chasms scaring the surface. There are these wonderfully huge cracks at the south pole of Enceladus, an expert describes. And as Enceladus orbits Saturn, these colossal cracks rhythmically open and shut, responding to the immense tidal forces exerted by the gas giant. These cracks are truly enormous, stretching for hundreds of miles. When they begin to open, you would have this big crevasse opening at maybe 100 miles an hour down the length of that. It would be incredibly spectacular. These immense gravitational forces from Saturn literally crack Enceladus's surface open and closed at astonishing speeds. Just like Io's elliptical orbit around Jupiter, Enceladus's orbit around Saturn is also elliptical rather than perfectly circular. This consistent, varying gravitational tug is what generates the internal heat necessary to melt the ice deep within the moon, creating vast, subsurface oceans of liquid water. The conditions within the water beneath Enceladus's surface are believed to be absolutely perfect for life. The temperature is just right, and the pressure would be suitable for biological processes. Crucially, this liquid water would be remarkably similar to seawater here on Earth. The chemical analysis of the water and other materials observed shooting out of these vents suggests a composition very much like our own oceans. It contains salt and, even more tantalizingly, organic material. This combination has led scientists to a profound conclusion. So we have identified a place in the solar system where there very well may be life right now. Cassini's instruments have, in fact, detected complex carbon molecules within the icy plumes erupting from Enceladus. When these complex organics are combined with the presence of liquid water, they strongly hint at the possibility that life, perhaps even thriving ecosystems, could survive deep within this enigmatic moon. And Enceladus may not be an isolated case. Another of Saturn's numerous moons might also harbor the conditions conducive to life. Titan, one of the largest moons in our solar system, and the only moon known to possess a thick, substantial atmosphere. Titan is a world of bewildering contrasts, a frozen realm where ice is as hard and unyielding as rock, and where vast lakes of liquid methane mirror Earth's watery bodies. Yet, even here, in this incredibly alien environment, we might find evidence of volcanic activity, and with it, the tantalizing prospect of alien life. The raging inferno on the surface of Io, the bewildering eruptions of ice and nitrogen on Triton. Volcanoes, in all their diverse forms, are one of the most destructive and powerful forces in our universe. But paradoxically, out of this annihilation, out of this profound geological violence, comes the very possibility of life. This holds true even on Saturn's mysterious moon Titan. It's a truly immense moon, spanning 3,000 miles across, making it larger than the planet Mercury itself. And, as mentioned, it is the only moon in our entire solar system with a thick, dense atmosphere. This atmosphere is so substantial that Titan experiences weather phenomena, storms, powerful winds, and even rain, though at temperatures so cold that liquid methane, not water, takes the place of precipitation and forms its surface lakes. Crucially, this atmosphere is also loaded with complex chemicals, the very building blocks that life, as we understand it, needs to survive. Titan has turned out to be absolutely one of the most interesting places in the solar system, a vibrant and active world. Its thick atmosphere, unique among moons, is remarkably similar to Earth's in its primary composition, being mostly nitrogen. And perhaps most excitingly, it turns out to be an atmosphere densely packed with organic molecules. Methane gas, high in Titan's atmosphere, reacts with sunlight, continuously generating the kinds of complex carbon-based chemicals upon which life fundamentally depends. But this raises a critical question. If sunlight is constantly converting methane into these organic compounds, why doesn't the methane in Titan's atmosphere simply run out? The atmosphere is full of methane, and yet we know methane is being destroyed by sunlight on a short time scale, so it shouldn't be there. A scientist explains, this implies there must be a continuous, active source of methane replenishing the atmosphere. Something on Titan is actively pumping out a constant supply of methane. Cassini, during its extensive mission, detected what appears to be a large crater on Titan's surface, its interior plunging to depths comparable to the Grand Canyon. Infrared cameras, peering through Titan's hazy atmosphere, revealed different types of materials surrounding this crater. Scientists believe that certain green areas observed could be volcanic in origin, perhaps vast plains of a strange, icy, lava, ejected from Titan's interior. If such lava exists, Titan-style, it would be a super-chilled, icy slush, likely composed of water ice, ammonia, or methane. Yet, compared to the overwhelming frigidity of the rest of Titan's surface, even this icy slush would be considered scalding hot. On Titan, the hot, Liquids spewing from these cryovolcanoes might be ammonia or water, substances that are normally frozen solid on the surface. But if they are heated beneath the surface by some internal mechanism, they could indeed erupt. The primary effluence from Titan's volcanoes, however, is believed to be methane and ethane. And that's probably the reason why we have this very thick cloud cover, this orange haze around Titan. A researcher suggests this haze probably came from outgassing from the volcanoes of Titan. Even for volcanoes on a world as incredibly cold as Titan, a source of internal heat is absolutely essential. This heat is what turns ice into liquid and generates the immense pressures required for eruptions. On Titan, this vital heat is thought to originate from two primary sources: the decay of radioactive materials within its interior, which provides a steady, low-level warmth, and the powerful gravitational massaging exerted by Saturn, much like the tidal forces at play on Enceladus. These two forces, working in concert, generate enough heat to melt ice into water and to transform liquid methane into gas, fueling the cryovolcanic activity. We think of volcanoes as being hot and ice as cold. A scientist notes, and yet if you're out on Titan, where you're a billion miles from the sun, and it's quite cold, then those flows of just barely above freezing water ammonia ice. They might be the hottest things around. This highlights a crucial point. So hot is a relative term depending on where in the solar system you are. Given these unique conditions, could volcanoes on Titan, despite their frigid nature, actually provide a chance for life to survive, even thrive? Life, as we currently understand its fundamental requirements, needs an atmosphere, a solid surface, liquid water, and sufficient heat to drive the complex chemical reactions that underpin biological processes. On Titan, it is conceivable that these cryovolcanoes could provide all of these essential elements. If you have a volcano on Titan, you'll have heat added to that, and all of a sudden you'll have liquid water surrounded by organic material. I mean literally anything you need for the start of life. One emphasizes, if life does indeed exist on Titan, it would truly be alien, fundamentally different from anything we know on Earth. It might, for instance, breathe hydrogen in place of oxygen, perhaps swimming through vast lakes of liquid methane at temperatures of 300 degrees below 0 Fahrenheit. Perhaps there are oceans of ethane, perhaps there are tide pools, and perhaps volcanic activity and hydrothermal activity. Perhaps there are hot springs. A scientist speculates the geothermal heat from cryovolcanoes could potentially generate enough energy to kickstart life in Titan's exotic environment. That's a speculation, but it can't be ruled out. However, we may not need to journey quite so far into the outer solar system to find tantalizing signs of life, or at least the potential for it. We might discover it on a volcanic world much closer to our own, the red planet Mars. Volcanoes, in their myriad forms, are truly ubiquitous across our solar system. Worlds like Titan, and Triton, once thought to be dead and inert, have been revealed as complex, dynamic, and often violent bodies. Once, humanity believed that Earth was the sole planet in our solar system possessing both active volcanoes and the miracle of life. Now, our probes and telescopes have uncovered volcanoes everywhere, a testament to the dynamic nature of planetary bodies. Yet, despite these widespread discoveries, we have yet to find definitive alien life. Volcanoes, in their raw power, embody the sheer forces of both creation and destruction, two sides of the same cosmic coin that often go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either, a scientist profoundly states. Indeed, in the fiery cauldrons of volcanoes, many believe, lies the very origin of life itself. Volcanoes are not merely destructive forces, they are fundamental architects of planetary landscapes, continually creating new terrain. They seed the atmosphere with complex chemicals, recycling materials, and replacing the old with the new. If volcanoes are so intimately bound up with the processes that enable life, then where, we must ask, is the life on these other volcanically active worlds? Perhaps the answer lies deep in time, in the ancient history of our solar system, when it was young, on a planet much like our own in its early stages of development. This is Mars, as it appeared 3 billion years ago. In that distant past, Mars was not the cold, arid desert we see today. It had active volcanoes, shaping its surface and releasing gases into its atmosphere. One colossal remnant of that ancient volcanic era still stands today, the largest volcano in our entire solar system, Olympus Mons. The sheer scale of Olympus Mons is almost beyond comprehension. The cliffs leading to its base are over 6 miles high. Mount Everest, the tallest peak on Earth, would sit comfortably within their shadow, and these are merely the foothills of this Martian behemoth. This is the awe-inspiring Olympus Mons. It covers an area the size of the entire state of Arizona. Its central caldera, the collapsed crater at its summit, alone measures an incredible 53 miles wide. A Goliath like this takes millions upon millions of years to build, a timescale that volcanoes here on Earth simply never get. On Earth, our planet's crust is in constant motion, divided into tectonic plates that slowly drift and shift. Deep beneath the surface, persistent hotspots push magma upwards, creating new volcanic islands, like those of Hawaii. But while the hotspot remains stationary, the oceanic crust above it is continuously moving, carrying the newly formed island away from the magma source. A new volcanic island then takes its place, leading to a chain of volcanoes. Mars, however, is fundamentally different. Its crust is locked solid, a single, unmoving plate. On Mars, there's just none of that tectonic activity. The crust is one big solid plate, a scientist explains. Consequently, if there's a hot spot, a persistent plume of magma rising from the interior, it just sits there and builds and builds and builds, and you get a bigger and bigger and bigger volcano. This geological immobility is precisely why Olympus Mons grew to such a gargantuan size. Today, Olympus Mons stands as a frozen relic, a silent testament to Mars's distant, warmer, and more geologically active past. Mars's atmosphere has since thinned dramatically, meaning that Olympus Mons, due to its immense height, now reaches almost into the vacuum of space. A true colossus, towering over the Martian plains. It is an extinct volcano on a dying world. But Mars's ancient volcanic terrain, specifically its colossal lava flows, could one day harbor life again, albeit a very different kind of life. The evidence for this intriguing possibility is found right here on Earth, in places like Hawaii. Here, volcanoes have created mysterious subterranean passages known as lava tubes. Natural channels left behind when torrents of molten rock surge into the sea or flow across the land. While many of these tubes are now collapsed or filled, some remain empty, offering a unique opportunity. Lava tubes are formed when an underground river of incredibly hot basaltic lava, around 2,000 degrees Fahrenheit magma, flows beneath a cooling, solidifying crust. Picture it like a frozen river of water with the ice crust forming on the top. It's the same thing, only here the crust is solid rock and the river keeps flowing underneath and makes this cave, this lava tube. A geologist describes. Extraordinary recent images captured by orbiting spacecraft strongly suggest that Mars's ancient volcanoes may also have created extensive networks of lava tubes. Any planet with basaltic volcanism, any rocky planet, will probably have lava tubes, a scientist asserts. And now we've found a couple of them on Mars in places where there are skylights, places where the roof has collapsed and you can see from orbit right into those lava tubes. If some of these tubes have collapsed, it stands to reason that many others are still intact, ancient relics of Mars's incredibly active volcanic past. Now, after lying dormant for perhaps millions of years, these subterranean lava tubes could potentially bring life back to the red planet. And that life, intriguingly, will be us. One of the formidable challenges facing future human inhabitants on Mars will be the harsh radiation environment. In particular, during intense solar storms, the cosmic rays bombarding the planet can be deadly. Having a storm shelter, a natural refuge beneath a substantial mass of rock, is truly the best way to protect yourself from cosmic rays. The network of tubes and caves formed by Mars's extinct volcanoes might one day make perfect homes for human colonists, providing natural protection. They could hold in precious air, shielding us from the deadly radiation that permeates the Martian surface. Thus, a long, dead volcano, a colossal monument to a bygone era, could paradoxically help fill a world with new life, serving as the very foundation of future human settlements. When we look at something as seemingly mundane as a car, it's astonishing to consider its cosmic origins. Every single atom in that car, from the iron in its frame to the carbon in its tires, originated from stellar explosions, from the magnificent supernova processes, and from the long, intricate journey of stellar evolution. These elements were not created all at once. They were forged at different times, in different stars, across the vast span of the universe's evolution. To truly comprehend how the universe meticulously crafted all the raw materials we observe here on Earth, we must embark on an incredible journey, traveling back through unimaginable distances of space and time to the very moment our universe was born. In the absolute beginning, there was truly nothing, no discernible space, no measurable time, no matter, no energy as we understand it. And then, in an instant, there was light. Suddenly, a tiny speck of light appeared, infinitely hot, infinitely dense. Within this unimaginably minuscule fireball, all of space, all of existence as we know it, was contained. This was, quite literally, the beginning of time itself. The cosmic clock began its inaugural tick. Time could flow, and space could begin to expand. At the very earliest moments of the Big Bang, if you trace it back to a theoretical t=0, everything in our universe, every galaxy, every star, every planet, all the matter and all the energy we can possibly observe, was once compressed into a region smaller than the size of a single atom. Today, the revolutionary idea that our entire universe was once so incredibly tiny originated from the brilliant work of the American astronomer Edwin Hubble, back in the 1920s. At that time, most astronomers firmly believed that everything visible in the night sky, every twinkling point of light, was simply a star, and that all these stars were contained within our own single galaxy, the Milky Way. But Hubble, with his keen observations and analytical mind, was not convinced. He meticulously studied a swirling cloud of light, known as the Andromeda Nebula. Through his groundbreaking work, he conclusively demonstrated that this nebula was not a cloud of gas within our galaxy, but in fact a vast, star city, in its own right, another galaxy, situated far, far outside the boundaries of our own Milky Way. Hubble's subsequent observations revealed an even more profound truth. These other galaxies were not stationary, they were actively speeding away from ours. And even more remarkably, the farther away a galaxy was, the faster it appeared to be receding. This observation led to an inescapable conclusion: the universe itself was expanding. And if the universe was expanding, then by logically tracing its history backward, it must have been smaller at some point in the past. Much, much smaller. And therefore, it must have had a definite beginning. The revolutionary idea of the Big Bang, though not yet fully formed, was thus born into scientific thought. Theoretical physicist David Spergel, a leading expert on the Big Bang, clarifies its scope. The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved. No one knows precisely what occurred during the absolute moment of the Big Bang itself. the singularity from which everything originated. However, scientists have a remarkably detailed understanding of what happened a mere fraction of a second after the universe was born. At that infinitesimally brief moment, this tiny, super, hot fireball was already beginning its stupendous expansion. We don't know the ultimate origin, the very genesis of the universe. So our scientific narrative begins when the universe was an almost impossibly young age, a billionth of a billionth of a billionth of a billionth of a minute old. An age that still challenges human comprehension. At this incredibly nascent stage, the universe was approximately the size of a marble. Less than a trillionth of a second after the Big Bang, this marble-sized universe, in a state of extreme instability, underwent an enormous, incredibly rapid growth spurt, a phenomenon known as cosmic inflation. During this period of unbelievably rapid expansion, space itself was expanding at a rate faster than the speed of light, carrying everything within it along for the ride. In a manner analogous to a hot glass ball inflating rapidly, the baby universe expanded in all directions at once. And as it expanded, it simultaneously cooled, its intense initial heat gradually dissipating across the ever-increasing volume of space. A mere trillionth of a second after the Big Bang, our nascent universe was still small enough to comfortably fit within the palm of your hand. A tiny fraction of a second later, it had grown to the colossal size of Mars. And another fleeting fraction of a second after that, the baby universe had already ballooned to an astonishing 80 times the size of the Earth. A trillionth of a second after the Big Bang, our newborn universe was still relentlessly expanding, but it didn't yet contain matter as we recognize it. At this incredibly early stage, it was pure energy, a seething cauldron of light and fundamental forces. Einstein's famous equation, E to mc d, which revealed the profound interchangeability of mass and energy, not only provided us with the theoretical knowledge to build weapons of mass destruction, but also, more profoundly, illuminated how the universe itself created its very first particles of matter. When a nuclear bomb detonates, a tiny, minuscule amount of matter is annihilated, irreversibly converted into a tremendous burst of energy. In the conditions of the baby universe, precisely the opposite process occurred. Pure energy, in an astonishing act of cosmic alchemy, was converted into particles of matter. However, there was a critical, potentially universe-ending problem. The nascent universe created not only matter, but also its arch-rival, antimatter, in almost equal quantities. And when these two fundamental opposites met, they instantly annihilated each other, converting back into pure energy in a brilliant flash. The infant universe, at this incredibly early stage, was a cosmic war zone, a relentless battle to the death between matter and antimatter. If they had mutually annihilated each other in perfectly equal measure, the universe would have remained forever full of energy, a sterile void devoid of any galaxies, stars, planets, or, indeed, life. Fortunately for our existence, there was an incredibly subtle, yet profoundly significant, imbalance. For every 100 million antiparticles that formed, there were precisely 100,000 Zalo-1 particles of matter. That crucial, tiny excess of just one extra particle of matter for every 100 million annihilation events was just enough to account for absolutely everything we observe in the universe today. This minuscule asymmetry, this delicate cosmic tilt, ultimately led to the existence of all the matter we see: the sprawling galaxies, the countless stars, the orbiting planets, even the intricate machinery of our cars, and, most miraculously, ourselves. Astrophysicist Carlos Frenk from Durham University in England elegantly explains, "We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this incredibly slight asymmetry between matter and antimatter, the universe would have been completely boring, There would be no structure, there would be no galaxies, there would be no planets. The conditions necessary for our existence hinged on this almost imperceptible cosmic imbalance. Precisely what this newborn universe was like, in its very earliest moments, has been a formidable challenge for cosmologists ever since the Big Bang theory was first put forward. Now, however, in one of the largest and most advanced laboratories on Earth, scientists are able to recreate conditions that almost certainly existed an instant after the Big Bang itself. This incredible facility is called the Relativistic Heavy Ion Collider, or RHICE for short, and it is located at the Brookhaven National Laboratory on Long Island. It is, in essence, a time machine capable of transporting us back to a mere 10 millionths of a second after the Big Bang. Here, scientists like Todd Satagaida accelerate subatomic particles, the fundamental constituents of matter, to speeds incredibly close to the speed of light. They then smash these particles into each other with immense force. The particles race around a 2.5 mile circular tunnel, traveling in opposite directions, completing 78 solos and circuits every single second. Finally, they collide head-on inside a giant detector, a colossal structure larger than a 3-story house. When these particles smash into each other, they generate incredible, instantaneous heat, mimicking the extreme temperatures of the real infant universe. We believe the early universe was extremely hot, billions of times hotter than the center of the sun, a scientist explains. And what you're doing when smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like. When the particles collide, they don't just bounce off each other. They break open, throwing out a shower of even smaller, more fundamental particles. It's a bit like trying to understand the intricate components of a car by repeatedly smashing them into each other. You can race 2 cars together and smash them into each other head-on, and when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, a researcher illustrates. And before long you can start to conclude that a race car is made up of these certain pieces. Through these high-energy collisions, the scientists at Brookhaven have made an astonishing discovery. Within these superheated, fleeting moments, a completely new and unexpected form of matter appears. And this matter contradicts previous theories about the nature of the early universe because it isn't a gas, it's a liquid. This primordial liquid was super hot, 100 million times hotter than the surface of the sun. There was so much energy packed inside the young universe at this stage that the particles vibrated with such incredible speed that had no stickiness. There was no friction, and it flowed perfectly. This liquid is described as perfect. It possesses no viscosity whatsoever. In a whimsical sense, it would be the perfect motor oil, except it's 1,000,000,000,000 degrees hot. Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second, a fleeting recreation of ancient cosmic conditions. The Brookhaven scientists have succeeded in recreating conditions that existed over 13 billion years ago, offering a direct window into the universe's infancy. Despite being a perfect liquid, this early universe was far from calm. It was a maelstrom of turmoil, teeming with subatomic particles ceaselessly smashing into each other, releasing ever more energy. There was so much energy, so much chaotic motion, that unless these particles eventually slowed down, they would never be able to bond and create atoms, the fundamental building blocks of all matter. And without atoms, the universe would never form galaxies, stars, or indeed, ourselves. The universe was now 1/1,000,000th of a second old and had expanded from being smaller than the size of an atom to a colossal 8 times the size of our entire solar system. After the incredible, violent turmoil of that first millionth of a second, the universe entered a relatively calmer phase. Over the next 3 minutes, the rapidly expanding cosmos continued to cool, reaching temperatures sufficiently low for protons and neutrons, the constituents of atomic nuclei, to finally bind together. This marked the formation of the first atomic nuclei, hydrogen and helium. However, these were not yet proper atoms. They were missing a vital ingredient, the electron. In the scorching early universe, electrons were plentiful, but the residual heat and energy were still so intense that the electrons were moving too fast to form stable bonds with the nuclei. And this state of affairs, with free floating electrons, would persist for over 300,000 years. At approximately 380,000 years after the Big Bang, the universe had expanded to the immense scale of our entire Milky Way galaxy. It had cooled dramatically, from billions of degrees Fahrenheit down to a mere few thousand degrees. As this cooling continued, the electrons finally slowed down sufficiently. The universe was now ready to make its first true, complete elements, as electrons could finally settle into stable orbits around the newly formed nuclei. One of the brilliant minds who serendipitously discovered evidence of this critical moment in the universe's story was Arno Penzias. In 1963, a then 30-year-old Penzias and his 27-year-old colleague, Robert Wilson, began work on a new, highly sensitive antenna at Bell Labs in Holmdel, New Jersey. Initially, their research focused solely on studying cosmic radio waves, but they were about to stumble upon one of the greatest scientific discoveries of all time. As they commenced testing their cutting-edge equipment, they detected an unexpected background noise, a persistent, unexplained signal that appeared to be emanating uniformly from all directions in the sky. They meticulously eliminated every conceivable earthly source of interference. We eliminated very carefully the ground, even the solar system, because we did this winter, to summer seasonal variation, man-made sources of equipment. All these things were eliminated, Penzias recounts. In desperation, with all conventional explanations exhausted, the two scientists began to entertain the rather unusual possibility that the strange signal might have an even more mundane, terrestrial origin. They discovered that a family of pigeons had taken up roosting inside the massive antenna, and it was thoroughly covered with their droppings. They wondered, however briefly, if the pigeons themselves, or their accumulated detritus, were the source of the persistent, mysterious signal. There was only one solution: the droppings and the troublesome pigeons would have to go. We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, Penzias humorously recalls, and we mailed them off to another site. But even with the troublesome avian inhabitants gone and the antenna meticulously cleaned, the mysterious signal stubbornly refused to disappear. And so, Penzias and Wilson were left with an almost inescapable conclusion: that this radiation was coming from the sky. I could not account for it. The strange, pervasive signal detected by Penzias and Wilson would ultimately prove to be one of the most important scientific discoveries of all time, providing direct observational evidence for the Big Bang. But the profound explanation for their mystery background noise begins not with sound, but with the majestic birth of light in the early universe. We typically take light for granted, a constant presence in our lives. Yet, in the early universe, some 13 billion years ago, had we been present, we would have seen absolutely nothing. Light, in those primordial conditions, was effectively trapped. The universe, at that unimaginably early stage, was opaque, like a dense, impenetrable fog. Imagine shining a powerful flashlight beam into a thick, swirling fog of smoke. The light bounces chaotically back and forth between the smoke particles, unable to travel freely, effectively trapped within the haze. In the hot, baby universe, a dense, ubiquitous fog of free, floating electrons acted as precisely this kind of barrier, constantly scattering photons and preventing light from escaping and traveling across space. But as the universe continued its relentless expansion and subsequent cooling, the electrons eventually slowed down. Protons, now able to exert their electromagnetic attraction more effectively, finally grabbed these calmer electrons, pulling them into stable orbits to form complete neutral atoms. First hydrogen, the simplest element, and then helium. With the electrons now bound within atoms, the universe was suddenly much less crowded with free, scattering electrons. The cosmic fog, in an instant, began to lift. Light was no longer trapped, it was free to hurtle out across the universe, creating a blinding, all-encompassing burst of light. Had we been there to witness this cosmic transformation, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift, and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment. A cosmologist describes. Over the immense expanse of cosmic time, this initial burst of light dimmed and cooled, its energy stretching as the universe expanded, eventually transforming into microwave radiation. It was this faint 13 billion-year-old microwave signal, this ancient echo, that Penzias and Wilson serendipitously picked up on their antenna. What they heard, in essence, was the quiet, persistent echo of the very moment the universe formed its first stable atoms, the fundamental building blocks of everything we see. It's really the light from the origin of the universe. To truly grasp the significance, consider this: if you have an old FM radio receiver and you tune it between channels where it doesn't quite capture and lock onto a station, you hear that characteristic static noise. That's what we call noise, a scientist explains. If you have a good radio set, 0.1% of that is actually the sound of the Big Bang. Similarly, if your television is not tuned to a station, that tiny fraction of static you see on the screen is, in fact, residual radiation from 13 billion years ago, a visual memento of the universe's birth. But this ancient radiation is not the only enduring reminder of the universe's genesis. Even the most common substance we interact with daily, the water we drink, carries a profound cosmic heritage. It's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms. A scientist marvels. Those hydrogen atoms, the simplest elements, were forged in the fiery crucible of the early universe itself. Over the next millions of years, the young universe continued its relentless expansion, gradually cooling and, paradoxically, growing dark again. So far, the universe had only managed to create hydrogen and helium atoms. But the rich, complex world we live in is made from more than 100 different kinds of elements, each with its unique properties. Without these heavier elements, the universe would have remained a very dull, monochromatic place, composed solely of gas, a cosmic void where complex matter, like planets, intricate machinery, and living, breathing people, could never possibly develop. To progress beyond this primordial simplicity, the universe needed to get its hydrogen and helium atoms to fuse into heavier elements. And to achieve that, it needed to make stars. The universe was now approximately 200 million years old and already billions of light years across. Its temperature had dropped so dramatically that it was colder than liquid nitrogen, reaching a frigid -367 degrees Fahrenheit. It was also profoundly dark, a vast, gloomy expanse filled with diffuse gas, but utterly devoid of galaxies, stars, or planets. This bleak scenario would have remained the eternal reality if it hadn't been for one crucial, inherent quality. The baby universe wasn't born perfectly smooth and uniform. Carlos Frank has developed an amazing 3D simulation that meticulously charts how the early universe evolved. It graphically demonstrates that when the universe emerged from the Big Bang, it was not perfectly even. Instead, Little cracks appeared which were very, very, very tiny, he explains. It was these minuscule imperfections, these subtle rushes, in the otherwise uniform fabric of the baby universe, that later developed into the grand, intricate patterns of galaxies and cosmic structures we observe today. Without these initial, tiny cracks, these subtle density fluctuations, the universe would indeed have remained a very dull, featureless place. The first crucial clues as to how these initial cracks developed into the vast structures of galaxies and stars emerged when other scientists began to examine the faint Big Bang radiation, the cosmic microwave background, first discovered by Penzias and Wilson. So what Penzias and Wilson saw was this radiation was, as far as they can tell, uniform, a cosmologist states. What cosmologists then dedicated themselves to for the next 25 years was an incredibly painstaking effort to try and find tiny, subtle variations within this seemingly uniform background radiation. And finally, they succeeded, using a specialized space probe called WMAP, the Wilkinson Microwave Anisotropy Probe. WMAP was specifically designed to detect and analyze, in exquisite detail, the minuscule variations in the cosmic microwave background radiation. Launched in 2001, this 150 million probe was equipped with some of the most sensitive instruments ever carried into space. While our eyes can only detect visible starlight, WMAP was tuned to perceive the invisible microwave radiation, the ancient echo of the universe's birth. Once in orbit around the Sun, it began to pick up the incredibly faint radiation that has been gently rippling around the universe since the dawn of time. So when we look at the cosmic background radiation, we're looking at this radiation that's been streaming towards us since 500,000 years after the Big Bang. A scientist clarifies. Initially, the microwave universe appeared very dull and seemed to be perfectly uniform everywhere. But when WMAP turned up the contrast, digitally enhancing the subtle differences, the results were nothing short of spectacular. The baby universe was not smooth and boring at all. It was teeming with tiny, yet profound, fluctuations. These tiny fluctuations tell us what the variations in density, how much stuff there is, and how it varies from place to place, a cosmologist explains. These slightly denser regions, these subtle clumps of matter, were destined to eventually collapse under their own gravity, forming the clusters of galaxies, the superclusters, and the galaxies themselves that populate our universe today. Conversely, the low-density regions, the subtle voids, would grow and expand, becoming the vast, empty spaces between galaxies. So this picture really is our connection between the universe when it was a baby 500,000 years old to the universe today, 13.7 billion years old. These tiny, almost imperceptible imperfections in the fledgling universe were the cosmic seeds that would ultimately grow into the magnificent galaxies and stars we observe. And this is one of the most amazing propositions in all of physics, the idea that galaxies like our Milky Way, each containing hundreds of billions of stars, once began their life as a tiny, infinitesimal crack or ripple in the very fabric of the early universe. The material within these slightly denser cracks was filled with swirling clouds of the newly formed hydrogen atoms. As the universe continued to evolve, the voids between these subtle gas clouds grew larger and larger, while the gas clouds themselves, under the persistent, gentle tug of gravity, became progressively denser and hotter. Gravity acted like an invisible sculptor, pulling these gas clouds together along vast, filamentary structures, much like beads strung along the threads of a colossal cosmic web. Where these giant filaments intersected and formed large, concentrated, globs of matter, stars and galaxies would eventually begin to grow. Over millions of years, as the universe matured, these diffuse gases were able to condense into more compact clouds, which in turn collapsed under their own increasing gravitational pull, leading to the formation of the very first stars. These nascent stars would eventually settle into rotating disks, structures that were later to become the majestic spiral galaxies, like our own Milky Way. Over immense timescales, the hydrogen atoms within these collapsing clouds clumped together, their increasing density causing them to heat up dramatically. At a critical point, the atoms began to fuse, releasing enormous amounts of energy, and the gas clouds started to burn brightly. Eventually, a star was truly born. All over the universe, across vast cosmic distances, millions upon millions of these first stars ignited for the very first time. The appearance of these primordial stars would have been a truly spectacular and transformative event, illuminating the previously dark cosmos. Had we been there to witness it, we would have really seen fireworks. Individual enormous flashes of light generated as the stars are born and bear themselves out. A cosmologist vividly describes, "The universe, having expanded many trillions of times its original size, was now suddenly filled with these newborn stars, primarily composed of hydrogen and helium. These young stars, however, were not quite like our own sun. They were typically much more massive, and crucially, very unstable. But it was precisely their instability that would make the universe a far more interesting and complex place, because deep inside the core of each new star, something truly amazing and transformative was happening. They were actively creating brand new elements. The revolutionary idea that stars are the cosmic crucibles where atoms are built originated from the brilliant mind of the British astrophysicist Sir Fred Hoyle, widely regarded as one of the greatest astronomers of the 20th century. Interestingly, Hoyle himself was a staunch opponent of the Big Bang theory, famously coining the term Big Bang in a somewhat derisive manner, believing the universe had no beginning. Regardless of his views on the universe's origin, Hoyle was deeply curious about a fundamental question: where did the elements heavier than hydrogen and helium come from? He theorized that stars acted like colossal nuclear reactors, operating somewhat like a hydrogen bomb in extremely slow motion, yet many billions of times more powerful. And in his groundbreaking hypothesis, the nuclear waste produced by these stellar reactors was, in fact, new, heavier elements. However, it would take years before scientists were able to confirm Hoyle's theory through direct observation. This confirmation came through the meticulous analysis of light emitted from stars. Each chemical element, when heated to extreme temperatures, emits light at a particular, unique frequency, creating a distinctive spectral fingerprint. Imagine a common sodium street lamp. It emits a characteristic yellow light, a color specific to the element sodium. The same principle applies to stars, but on a vastly more complex scale. If you break down the light from our sun, for instance, into its constituent spectrum, you can observe distinct lines, much like a cosmic barcode, each corresponding to the presence of specific elements. Each element has its own set of specific colors and wavelengths, allowing scientists to identify elements like hydrogen, which primarily emits red light.